Hello, this is Monika Sommerhalter. In this video, I will walk you through the data analysis of the Bradford experiment. On the left is the data exported from the NanoDrop instrument, and on the right are two data tables that you can generate from the data of your lab notebook. Bovine serum albumin, abbreviated BSA, was used as the standard. The concentrations ranged from 0 to 1 milligram per milliliter, and the corresponding absorbance values recorded at 595 nanometer are listed. Banana pulp extract was prepared in different dilutions, was used as is, 10-fold diluted and 5-fold diluted. These 5-fold dilutions were prepared independently of one another. Step number 1 of the data analysis is to generate a standard curve. We will insert a scatter graph, and the scatter graph has to be in individual data points because you measured individual data points. On the x-axis is the concentration of the bovine serum albumin in milligram per milliliter, and on the y-axis you have the absorbance readings. You need axis titles, else nobody will know what you displayed on your axes. So the y-axis was absorbance at 595 nanometer. Please note that absorbance itself has no unit, and the specification of nanometer is for the wavelength. On the x-axis, where you have the bovine serum albumin concentration, it's important to specify the unit in milligram per milliliter. It's up to you whether you want to keep the grid lines. If you only have one type of data displayed, it doesn't make too much sense to have a legend. Chart titles are typically not displayed in publications. It can help for your very first draft of a data analysis, however. So next is to incorporate a standard curve. So I'm adding a trend line, and this trend line shall be linear. I'm not going to choose an intercept because we didn't blank with the Bradford reagent. The blank was just water, and the Bradford reagent itself absorbs light at 595 nanometer. But we need the equation and the correlation coefficient, or R-squared value, on the chart. Another way to get to the slope and the y-intercept of this standard curve is to use some functions in Excel. So, for example, the slope, I can use the function equals slope. Then I'm going to select the known y's, which are the absorbance values, the known x values, and I'm getting exactly the same number, the 0.635, and here with way too many digits. So if I want to restrain my digits to something more reasonable, maybe more digits for now, because we're still making calculations, than the significant digits, but not necessarily 8. To get the y-intercept, the function is actually called intercept. Again, selecting the known y's and the known x. And I'm extracting the digits. Excel also has another useful tool. It's called the line estimation, and it's an array function. So a line estimation, let me first explain, label it. So I'm using linest, so equal linest. I'm going to select the known y values again, my absorbance values, followed by the x values. Then I can decide whether I want to force this trend line through 0 or calculate a y-intercept. And since we will calculate a y-intercept, the curve does not go through 0, I'm selecting the keyword true. In addition, my last entry for that linest function is to return additional regression statistics. So I'm also going to type true. Since linest is an array function, you can see that I got more than one entry here. So to interpret the outcome of linest, you probably already realized that this first entry here is the slope, and the second entry is the y-intercept. Also, this number 0.99 might look familiar to you. That was the R-square value. Other statistical parameters are the degrees of freedom, 5 degrees of freedom because we had 7 value pairs and 2 parameters x and y, or slope and y-intercept. And the rest of the linest functions are returns from a full statistical analysis of that fit. One of the benefits of using this function linest is that you get the error of the slope and you can get the error of the y-intercept. And this might come in handy later, but it's actually more than you need to know for this experiment. What we need for this experiment, what we need in order to continue with the data analysis, are the parameters of the standard curve, the slope, and the y-intercept. We use the bovine serum albumin as a standard, and we make the assumption that the proteins in our unknown sample will have a very similar color response. So for our unknown sample, the banana pulp extract, we only have the absorbance values, and we want to use these absorbance values and the standard curve to figure out the protein concentration in the banana pulp extract. Without doing a calculation, you can already see that the undiluted banana extract with the dilution factor 1 is very close in its absorption value to the standard with a protein concentration of 0.8 milligram per milliliter. So you should have the expectation that your banana pulp extract will have a protein concentration roughly similar to the 0.8 milligram per milliliter. I'll now use the data of the banana pulp extract to calculate the protein concentration based on the bovine serum albumin standard curve. So the protein content in units of milligram per milliliter. I'm pressing an equal sign into this cell to enter a formula. The absorbance value is on the y-axis. And in order to apply this formula, I first have to solve for x, and I want to apply this formula and solve for x. So I first have to subtract the y-intercept. I could either type in this value, or since I set aside these values of the calibration curve, I can click into the cell. And since I want to use that cell more than once for all the data manipulations, on my keyboard, I'm going to select the F4 key. F4 changes the format of this cell entry. You can see the $2 signs appearing around the letter C, and the letter C is for the column position. Then I close the parentheses and divide by the slope. Again, I could simply enter the value or select the slope, and I might press F4 again or manually $2 signs around the column position C. The advantage of pressing F4 or labeling a cell by surrounding its column position with $2 signs is that if I now pull down on the corner, these cell positions for the slope and the y-intercept are not changing. Let's double check. If I click into one of the cells, you can see how all the manipulations are performed with C21 for the y-intercept and C20, the cell for the slope. All these numbers in this column have way too many digits. If your absorbance values only were measured to 3 digits, you can't suddenly have a higher accuracy in your calculated value than what your measurement provided you with. These already are the protein concentrations of the diluted sample. Next, it's important to take into account the dilution factor. And in this case, I can simply multiply my protein content of the diluted sample with the dilution factor. In theory, all these values, after I take into account the dilution factor, should be identical, but they're clearly not. So it's time for some statistics. So if you want to get the average value of all your measurements, you can use the function average. And then standard deviation, too many digits. The average has the same units as the individual values, and so has the standard deviation. It can be informative to form a ratio between the standard deviation and the average, and that ratio is called the coefficient of variation, or CV value, and it's typically given in percent. So if I form this ratio and turn it into a percent value, good pipetting technique is typically considered if your coefficient of variance is less than 5%. 6.5% is a bit too high. Also, when I look at my standard curve, not too happy with the 0.4 milligram per milliliter standard kind of lingering above the curve, but it's a real experiment.